Okay, we finished last time talking about the shapes of proteins and their functions of proteins. Now I'm going to talk specifically about a particular type of protein called an enzyme. Now, when we talked about chemical reactions before, we drew a chart. We drew a graph where the reaction and the energy, and how a reaction needed a certain amount of energy. So we have the products, so we have the reactants, and we have the products going along, and this energy to get the reaction to actually occur is called the activation energy. Okay. There are some instances which we need a reaction to go very quickly, but the activation energy is so high that it can't go quickly, it'll go slow. What an enzyme does is they speed up the rates of reactions by decreasing the activation energy. So this is activation energy with an enzyme. Okay, so this is going to give us a couple of rules for enzymes. And the first and most important one, and I'm going to put it in red because it's so important, is an enzyme will not cause a reaction to occur that would not normally occur. Okay, so if you have something in your body and the two things will not normally react, or it will not normally break apart or normally come together, an enzyme will not magically just snap its little protein fingers and cause it to happen. It's just never going to happen. Okay, so an enzyme will only cause a reaction to occur that would normally occur in the body. Okay, so how enzymes work. So we're going to do this in a very generic fashion. So let's say that we have two molecules. One is shaped like a square, and one is shaped like a funky diamond. And in nature, in your body, a reaction will occur that will combine these two together. So we will get a larger substance. Okay, so you use your imagination. So say we want to build a sugar, we need to put the sugars together. Okay, we want to build a protein, we need to put the amino acids together. Okay, those will happen. This reaction, we're going to say this reaction will happen naturally in the body, but let's just say that the energy required is enormous, and so it's a very slow process. But what we can do is, if I need this reaction to happen quickly, is the body will make enzymes to do this. And so what an enzyme is, we already said it is a protein. It is a globular protein that has parts, that has little sites, active sites that resemble the molecules in question. So what the enzyme is going to do is, where this reaction is occurring, the enzyme is just going to float around willy-nilly, okay? And it's going to pull up these molecules. And so these molecules will fit inside of, sorry, let me do it black. The molecules will fit inside these enzymes, okay? And what we have when we have these molecules bound inside of these enzymes, it's called the substrate complex. It's the enzyme substrate complex, because we have the enzyme here. These are called substrates for the enzyme. And when you put them together, it's an enzyme substrate complex. I mean, that's just, why can't they just say it's a full enzyme? I mean, I just wish they would simplify language sometimes. So then what this enzyme is going to do, it's going to do the chemical reaction. It's going to make the chemical reaction occur. So when these two, in nature, what's going to happen is these two molecules will combine. What the enzyme does is it combines them. The enzyme will automatically combine them, and then it will kick them off, formed the way they should be, as if it occurred naturally. However, it just sped it up to what, let's just say that this reaction takes 5 minutes to occur. An enzyme could probably make it happen in a second. Okay, that's how fast enzymes work. Okay, so this enzyme, the neat thing about this enzyme is it will only act on these substrates. It will only act on these substrates. If I get something that's shaped like a square and a triangle, this enzyme won't work on it because they don't fit inside that enzyme. And that is rule number 2. Enzymes are specific. Enzymes are very specific. So let's just say an enzyme that you use all the time and not aware of it is this one called amylase inside of your saliva. So that is very specific for sugars, specific types of sugars, glucose, and it's a sucrose, and it'll break it down into its component parts, and it allows you to taste sweet. It's the amylase that allows you to do this. Amylase is very specific to sugar. It's not going to break down proteins, and it's not going to break down fats. Okay. In order to do that, you need a different enzyme. So if I have an enzyme that will break down sucrose, that enzyme isn't going to break down maltose or lactose. Okay. I need an enzyme to break down maltose. I need an enzyme to break down lactose. And that's what specificity means. An enzyme will only work on certain substrates. That is it. Okay. Another thing is that enzymes can be limited. Okay, enzymes can be rate limited. So this means if I have an enzyme, and an enzyme, one single enzyme. So let's just say I have a million. Let's just say I have a million substrates that are eventually going to make 1 million products. Okay, and if I put an enzyme in here, and that enzyme will do one reaction every second, that means that enzyme will take 1 million seconds in order to get this done. Okay. Now, if you put in more product, so if let's just say I need to go faster, if I put in 1 million more, the enzyme isn't going to go any faster. You can't do it. The enzyme can only go as fast as the enzyme can go. The only way to overcome that is to add more enzyme. Okay. And that's what we mean by it is rate limited. The enzyme can only work as fast as the enzyme can work. You can't do anything to make the enzyme work any faster except add more enzyme. So if I had an enzyme, let's just say here, let's get all of this extra stuff out here. If I had an enzyme, let's just say this enzyme is 1 reaction Rxn per second. Okay. If I wanted it to get done in half the time, I'd have to add twice as much enzyme. So if I wanted to get it done in 500,000 seconds, I'd have to double my enzyme. If I wanted to get it done in a quarter time, I'd have to put 4 times as much. Okay, so that's what it means. Enzymes can be rate limited. And so what you see is enzyme, and it's actually a really neat equation. So enzymes, they actually peak up. You can saturate an enzyme, and this is called the saturation point. No matter what you do, the only way you can actually increase the rate of reaction is by adding more enzyme. Okay, and that is the saturation point. So that's rate limited. Okay, the other thing about enzymes is they are catalysts. Okay, what this means is enzymes are not changed in or by the reaction. Okay. So if I have an enzyme that like breaks apart molecules. So let's just say amylase, for instance. So the amylase is going to break the sucrose into fructose and glucose. As soon as it's done with that, it's going to grab another one and break it again. It's going to grab another one and break it again. The enzyme is not changed. It will just go and do its thing. Go and do its thing over and over and over and over again. Only the products and only the reactants are changed in a reaction. The enzyme itself isn't. And the reason is because it is a catalyst. Catalysts do not change. They just make the reaction occur faster. Okay. And the fifth thing about enzymes is they can be denatured. Okay. And denatured means made to not work. Made to not work. And usually what happens is you unfold a protein and it will not work. It will not work. It will not work as intended. And the best way to think about denaturing is you've all fried an egg. The whites of an egg are the protein part. The yellow of the egg is the fat part. So when you fry an egg, you put it in that heat, and that heat turns that egg white. Literally white. It's usually this slimy clear snot consistency thing, and when you heat it up, it becomes white and it becomes very solid. What you've done when you fry an egg is you denature the proteins. Now a lot of times in the body, if you denature a protein, if you put it back to normal, the protein will come back. Okay. In the case of an egg, that is forever denatured. It's never coming back. But that's what it is. Denatured just means to be made inactive. So now, what can affect the rates of enzymes? Okay, so number one, and the most important, is increased temperature will increase enzyme speed. Now, this is how I want you to think about this. I don't want you to think about the enzyme just works faster. No, the enzyme does not work faster. When you increase the temperature, what you are doing is you are increasing the speed of individual molecules. Okay. Now, here's how I want you to think about it. So let's say I have a space. Let's say I have a space right here. Okay, in here. And in this space, I have just these floating molecules, or whatever you want to call them, and in here also I have an enzyme that will work on these molecules and will cause some kind of reaction. Okay, now if these molecules are moving slowly, that means there is a very slow chance that they will actually bump into the enzyme. And this is how this works. Okay, the enzyme doesn't know where to work. The molecules don't know to go into the enzyme. It's all random chance and it's all random bumping. And that's all it is. So if I have something that is solid, frozen solid, and there's no movement, the enzyme is never, ever going to work because the molecules can't bump into it. But if I add more temperature into the system, that means I move the molecules more. And when the molecules move faster and the molecules move more randomly, there is a greater chance for them to actually hit and bind to the enzyme so the enzyme can do its work. Okay. Now, there is a caveat to this. Okay. If temperature gets too high, the protein will denature. Okay. So there's a trade-off. Okay. Increasing the temperature will increase the rates of reaction just because it increases the random motion of the molecules, because remember, it's all just chance. It is all just random chance. But if you get just because you're increasing the rate of reaction, you can increase the temperature of reaction. You can increase the temperature to the point where poof, the enzyme doesn't work anymore because you denatured the enzyme. So there is an extent. But in general, it's safe to say that increased temperature increases the rates of reaction to a certain extent. Okay. Increased pH changes in pH will also alter the changes in enzyme activity. Typically, decreasing pH will increase enzyme activity. To an extent, again, if something is too acidic, if something becomes too acidic, the reaction will stop because you denature the protein. Okay, and the same thing. If you increase the pH too high, the enzyme will denature and it won't work. Okay, so that's it. The takeaway, what I want you to just take away from this: enzymes, what are they? They're catalysts. They increase the rates of reactions because they lower the activation energy of the reaction. Okay, enzymes are substrate specific. That means they will only work on certain things. They're not universal. They're not universal. If I need a reaction to occur, I have to have an enzyme specific for that reaction. And if I want another reaction to occur, a different reaction to occur, I have to have an enzyme that is specific for that reaction as well. Okay? Enzymes can be denatured. They are catalysts. They are rate limited. You can saturate them. And temperature will increase the rate of reaction to a certain point. Decreasing pH will increase the rate of reaction to a certain point as well. Okay, so that's all I want you to know about enzymes. Okay.